Continuing with our example using our glass beads, we first poured water from the graduated cylinder into the cylinder containing the beads with a total volume of 100 cubic centimeters. We used the water remaining in the cylinder to determine the amount of water that was held in the beads, which was related to the total porosity of the container. So in that case, 42 milliliters of water was held in the beads, which means that 58 milliliters or cubic centimeters of the space in that cylinder was occupied by the solid particles, the beads. Then we took the water and we poured it from the beads back into the graduated cylinder. And when we did that with our 25 millimeter glass beads, almost all of the water went back into the graduated cylinder. With the 10 millimeter glass beads, it was a slightly different story, but most of it came back. With the 5 millimeter glass beads, again, a little bit more stayed in the beads. And when we got to the 1 millimeter glass beads, a fair amount of water actually stayed in the beads. So what we see is the smaller pores held on to more water. So again, this is not about total pore space. Now we're talking about the size of the pores. So let's go then and look more about our calculations that we need to do when we're going back this direction. So first, we put 58, there were 58 milliliters of water remaining in the cylinder when I poured water into the 25 millimeter beads. Now when I poured the water back from the beads into the graduated cylinder, now I have 99 mils of water here, 98 in this case, 96 in this case, and 89 in this case. So the water recovered then is the difference between those two numbers. So 99 minus 58, 99 minus 58. Well, what that's equal to 41. What does that mean? That means that 1 milliliter of water is still in the pores. You do the same process with the others. I'm going to do the 10 millimeter and allow you to do the other two on your own. In this case, 98 minus 44. Well, if we do 98 minus 44, what do we get? We get 54. So we recovered 54. That means, in this case, when we're looking at this, we have 2 milliliters or cubic centimeters that are left in the pores. In this case, we had 96, so we ended up with 44 here. That we've poured back, and 4 milliliters there. And in this case, we had 41. Math right here. No, 31. 31. And we had 11 milliliters that remained in the pores. So our water-filled pores then, we're calling that VW. This is our water-filled pores. The water remaining in the pores, and value is in milliliters, and so that is the volumetric, the volume of water in the pores. And since 1 cubic centimeter is equal to 1 milliliter, that is 1 cubic centimeter. That's water-filled pores. Now, the next thing that we have then, we want to know, we have the pore volume that we got from the previous slide. And now we want to do the volumetric water content using the definition formula. If we think about our cube again, the volumetric water content, we did that previously. And the volumetric water content by volume is equal to the volume of the water divided by the total volume. The value is going to be in cubic centimeters per cubic centimeter. So what do we end up with? In this case, the water that was remaining in the pores is 1, and we're dividing it by 42, or by 100, which was the total volume. Cubic centimeters. In this case, we have 2 divided by 100, 4 divided by 100, and 11 divided by 100. Because we're just taking our values and plugging them in. VW, VW, and VT is 100. So we get 0.01, 0.02, 0.04, and 0.11 cubic centimeters per cubic centimeter. So what's the next thing that we need here? Now then, we get to this point of degree of saturation. As we did before and talked about that before, this is the quantity of the pores that are filled with water. So at this point, what we need is the volume of water, using our definition formula. The volume of water, we divide that not by the total volume, but now by the volume of pores, and we're going to multiply by 100 because the answer is in percentage. So what do we have now? We have a volume of water. In this case, it was 1, and our pore volume was 42 for this one. So where were we finding our numbers again? Well, we found our number. The volume of water is here. And the volume of, so that goes here. And then the volume of pores is this. That's what goes in the denominator. So we had 1 and 42. We have 2 and 56. Let's go back to black. We have 4 and 48. And we have 11. And we have 11 and 42. At this point, it's time to use our calculators. We've got something that's on the order of 2.5% on the low end, up to a little bit more than 25% on the high end. And that's a 12th, that's a 28th, so that's going to be a little bit less than 2%, and then this one's, that's going to be a little bit less, maybe around 8% or so. But now's the time for the calculator. When we do our calculations, we find 2.4%, 3.6, 8.3, and 26.2. But when we go back and review our protocol, we see that the precision is in to the nearest integer, 1%. So we're going to round these to 2%, 4%, 8%, and 26%. Now, since I use the percent sign up here, I really do not have to put it with each of these values in the table. So I'll get rid of our percent signs here. And when we've done that, now we've finished our data set on a volume basis for pouring the water into the beads and seeing how much water moves into it, so the volume of the pores, and then pouring the water back out of the beads into the graduated cylinder to see how much water stayed in the beads, and calculated the saturation percentage in both cases. The next set of information we'll run through similar calculations, but using the mass of the water and the mass of the beads, as opposed to using the volume basis.